and length d equal 0.75 lambda. So find total V of z and I of z on the line for 0 less or equal to z less or equal to d. All right. In this one, I will assume that the line, transmission line, is excited by an ideal voltage source. All right, and then V of t equals V naught cosine omega t, where, okay, that's it. And lambda is where, I'll put here, where F times lambda equals C in this case. So the lambda I gave you is that lambda. All right, so solution. First of all, I'm gonna draw the line, the transmission line. So here, the normal way we do that. In fact, we're gonna solve this problem this time, as I said, using paper, and then we will do the same problem using the Smith chart. So here, we'll duplicate that. All right, so we place at the end the load, and I use a thin line for this. So ZL normalized. Obviously, I gave you a normalized load. So what is it that I'm not giving you characteristic impedance? You do not need it unless, you know, I go later. But at this point, we are so far so good. So ZL equals 2. Then we know that the line has a length d. So if I am to write a coordinate system z, then this is going to have z here equals 0 and z here equals d. And now I'm going to put the symbols in the input and output ports of the line. So the left side is called a port, and the line is called a port, all right? And then, so the left side is the input port, the output side is the output port, the output end. So this is the input port has A and A prime here. And then I will just put here the input port. And usually it's A prime. And then here is B prime. And that's the output port. So it's B prime. And also remember that when we do that and we want to look at some location Z, so I'm going to place myself at a Z location, all right, randomly between the input and the output ports, and then I will call this C and C prime. And remember, then when I do that, I call this to be Z, and I call this one to be Z prime. All right, both positive numbers. Now, okay, the source is on this side. Let me in fact do it a different color. The source is on this side. And since I am now in the phasor domain, I will put for the source V naught. And let's assume that V naught here is 1 volt. All right. Okay, so now we're gonna just write things. We're not gonna use the Smith chart at this moment. So it's A. What do we know? We write all of the expressions we know about V. We know that V of Z is made out of two parts. V plus of Z, which we call also the incident wave, plus V minus of Z, which we call the reflected wave. And this is, the incident wave is V naught plus e to the minus j beta Z. And the reflected wave is V naught minus e to the j beta Z. All right? Also, let's write about the current. To remember, the current has the same two waves, an incident and a reflected. But then we have found from our expressions that in terms of V naught plus and V naught minus, we can write it as V naught plus divided by Z naught, e to the minus j beta Z. Obviously, to find that, you need Z naught, minus now V naught minus divided by Z naught, e to the j beta Z. And remember this here. You have to remember that for I of Z, I have a minus sign. Why is that? Because we have defined the V plus and V minus, V0 plus, V0 minus, I0 plus, and I0 minus. So by definition, we have stated that V naught plus divided by I naught plus is Z naught, and V naught minus divided by I naught minus is minus Z naught. We have postulated these two, all right? Nothing derived those for us, we just postulated them. Okay, so now, what else do we know? We know, because we are looking first of all at identifying an expression for V of Z. All right, so what else do we know? I'm gonna write down. I know that gamma of Z is equal to gamma L e to the minus j beta Z prime. We know that. And I know that gamma of Z is nothing else but V 0 minus, excuse me, V, sorry, is V of Z minus V plus of Z, all right, and V minus, and from there also, I can find out that I find the previous relationship, or, all right, so it comes from this definition. So practically, just to remind you, this is coming from that. All right, so this is what we know. And then also we know gamma L. How much is gamma L? Gamma L is ZL normalized minus 1 over ZL normalized plus 1. And from this relationship, these two relationships there, also I find out that gamma L, so in fact, let me show you, yeah, well, let's leave that there, just leave it for a moment. We don't need any more relationships, that's enough what we have. Oops. All right, so from there, we have that gamma L is equal. Now, why are we going to use practically gamma L? You can use it for the following reason. I mean, if you go up there So obviously from that relationship, later, let me find gamma L first of all, and then we will plug this into the relationship and then put it up there. Okay, so what do we have? That gamma L is gonna be 2 minus 1 over 2 plus 1, so it's gonna be 1/3. So practically it's gonna be 0.33. Right? So what happens is I have two waves that are coming my direction. One is the incident. Now I'm sitting at this CC prime, all right? So one is an incident wave that comes the voltage, and voltage applies between the two, all right? You need to remember that the voltage, V of Z, that we wanna find, applies here like that, all right? And I of Z goes like this. And this here, of course, the same, goes back, as we said. But we are looking at V of Z and I of Z. Okay. Now, let's try to figure out how much, there are two things you can do, obviously. One is to find the relationship between V0 minus over V0 plus, and then go here and substitute one of the two with the other, or so you can either go here and replace V naught minus and V naught plus, or you can go here directly, all right? And we can do that. So if we go, well, you can select anyone, but since we have this one here, this relationship there, okay? Since we have that, I can use this and rewrite V of Z, obviously. I can rewrite V of Z as V plus of Z, and then is 1 plus V minus of Z divided by V plus of Z. And that is going to give me what? V plus of Z to be times 1 plus gamma of Z, which is going to make it equal to V plus of Z. And then inside here, I'm going to have 1 plus. So gamma L, which is 0.33, all right, I got that, E to the minus J beta Z prime. All right, how much is Z prime? Z prime equals D minus Z. You agree, all right? I mean, because the sum of the two, the way we have identified them, the sum of the two equals D. So here is what I'm gonna do next to it. E to the minus J beta Z equals to E to the minus J beta D E to the J beta Z. All right, and as a matter of fact, I should have 2 here because, which I've left. So I should have a 2 here. Let me put a 2 because you see why I left these 2 out? I should have it because of how I take the 2 expressions. Okay, then what I have to is, I put a 2 there, correct? Just want to make sure. Minus J2, and there we have to put a 2 everywhere. So 2, well, J2 is J2 beta D minus J2 beta Z, a plus we said here. Okay, and the other was a minus. And then we had a minus in front. All right. So how much is beta D? 2 beta D. 2 beta D is 4 pi divided by lambda, and D is 0.75, which is 3/4 of lambda. All right. So that gives 3 pi. And therefore, e to the minus j 2 beta z prime is nothing else but e to the minus j 3 pi e to the j 2 beta z. So how much is e to the minus j 3 pi? E to the minus j 3 pi is cosine of 3 pi minus j sine of 3 pi. This is 0, and that is minus 1. Okay? So this one here gives me minus e to the j2 beta z. And that is important relationship. All right. Now, if I call this one, and if I call this 2, what I have is v of z equals v plus of z. And then inside here, I'm going to have 1 plus 0.33 e to the minus 2 beta z. Now I'm going directly to have a z component because I want to plot it across z, all right? Okay, and a minus in front because I found a minus there. I have a minus here. Now, practically, I have an expression for z here. And v of z is a complex number. How do we plot complex numbers? Usually, we care about their magnitude, first of all right? So when somebody tells you, show me how v of z changes in a line, I would start with the magnitude. So I would say, okay, let's find the magnitude of v of z. And the magnitude of v of z will be the magnitude of v plus of z times the magnitude of this complex number, which is magnitude of 1 minus 0.33 e to the j 2 beta z. All right? How much, all right, let's plug it in. How much is v plus of z? Is v naught plus e to the minus j beta z. All right? And 1 minus here, 3 e to the j2 beta z. This is a product here. You see that one? It's a product of two numbers. One is a complex e, the other is a constant. And so I can rewrite this as the magnitude of v plus, magnitude then of e to the minus j beta z. How much is that? How much is the magnitude of this? Let's think again.
The magnitude of the second term?
Yes.
Magnitude of 1.
1. The magnitude of the exponential of jb beta z is 1. Okay?
Oh, you're talking about the first. Okay.
That one.
Yeah.
The yellow one.
Yeah, because those are separate. Okay, I think you meant the 1 minus.
No. I mean the yellow one. Okay. So this one, is 1. So practically I get V naught plus, and then I have this one, 1 minus 0.33 e to the minus 2 beta z. Okay, so look what I'm gonna do. I'm gonna find V of z as a function. I will take this ratio, the constant, and then, so practically the only thing I have to do is to find the magnitude of this complex number, which is going to be, if I write this complex number a little more carefully, so I'm doing it extremely slowly and clearly so you see the details, is 2 beta z minus j sine of 2 beta z, which in fact gives us the magnitude of 1, let me see, it's 1 minus 0.33 cosine 2 beta z, all right, and that's your real part, minus j 0.33 sine of 2 beta z. Let me move this just a second, move that here. 2 beta z. All right, which in fact, we have that V of z over V naught plus of z, this one, is equal to square root of 1 minus 0.33 cosine 2 beta z, all right, square plus 0.33 sine, let me put it here, of 2 beta z, and that square. Okay? So now this is equal, I will continue to 1 minus plus 0.33 cosine 2 beta z, and that square, minus 0.66 cosine 2 beta z, and in fact, because I don't want to do it like this, I will put something like that, to 1 over 2, all right? So practically, it's better if we write it like this, 1 over 2. Okay, because now I don't have to write this square root this far away. So this one, and then plus 0.33. I don't have enough space. So I will write it here, plus 0.33 sine of 2 beta z square. All right? And so I did this. And then, so I'm claiming that this one gives me 0.33 squared. So from here, we have 1 plus, do you agree with me that these two together give me 0.33 squared? Because the first one is going to be 0.33 squared times cosine squared of 2 beta z. And the second one is going to give me 0.33 squared times sine squared of 2 beta z. So it's going to give me 0.33 squared, and inside I'm going to have a cosine square of 2 beta z plus a sine square of 2 beta z, which makes this to be 1. All right, and then I have the rest, which is minus 0.66 cosine to beta z, and all of this 1 over 2. So practically now, to just summarize, I found that V of z divided by V naught plus magnitude is this one. How much is 0.33 square? Let me see. 0.33 times 0.33. Yes, 0.1089. 0.1089 plus 1, all right, from there, minus 0.66 cosine of 2 beta z. So that gives me 1.109 minus 0.66 cosine of 2 beta z, and that's 1 over 2. Okay, that's practically how it changes. It's not obvious how it changes, all right? But it changes like that. So how are we going to find exactly how that goes? Since we have cosine to beta z, and since from when z equals 0 to beta z equals 0, when z equals 0.75 lambda, which is 3/4 of a lambda, then we have the 2 beta z is going to be 3 pi, if you remember. All right, so between 0 and 3 pi, we have to find this function v of z. So practically, I'm going to take z, and then instead of z here, put here this function. Instead of z, I will put here 2 beta z. So I'm going to have 0 pi over 2 pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi. All right, so practically, this is my length, the length of my line. So I can put it here so you can see it. Yeah, that is my line. And in fact, the line here, it's not only one, is 2. So this is my line, as you can see. And I will plot the impedance there. The voltage there. So what I'm going to plot is this one, V of Z. What I'm going to plot is this one, V of Z. Divided by V naught plus, which is a constant. All right, along this. Okay, let's see. So cosine to beta Z varies from 0 to 3 pi. So obviously, from 0 to 3 pi, it goes through minima and maxima. So the minimum of this function happens when cosine to beta z gets its value of 1, because that's when you subtract 0.6, the largest number, right? In fact, when it gets positive practically, when cosine to beta z becomes 1, you get a minimum. When cosine of 2 beta z becomes minus 1, you get a maximum. All right, so here, for example, you're going to find, so let me move a little bit this one below to leave some space. And so from here, we have that V of Z, V naught plus, has a maximum value, V of Z, normalized to V naught plus, maximum value of what? Of the square root of 1.109 plus 0.66 which in fact makes it, let me here, plus 1 here, plus 0.66, and find the square root of that. 1.33, and we get a minimum value to be equal to square root of 1.109 minus 0.66, which is what? Let me find it. 1.109 minus 1.1 1.109 minus 0.66, and then square root of this, 0.67. So 0.67. Okay, did I do right? 1 minus 1.1. I think I've made a mistake. 1.109 minus 0.66 equals 1.109 minus 0.66 equals, and then I do the square root. Yeah, all right, so it's 0.67. So, and then it alternates between the two. So if I were to plot it, and in fact, as I told the other class, I would like you to plot this, go to MATLAB or go another, and then plot this expression that I gave you, that we have calculated, and then I will place it like a small exercise, not through Top Hat. I will do it through Canvas, and then you just do it and then take a picture and upload it. All right, just as a little exercise. So what you're going to find is when beta z goes to 0, what did we say? When it goes to 0, this gets its highest value, so it gets the minimum. All right, it goes to a minimum. And then when it goes to -1, it goes to maximum. So it starts at a minimum, which is 0.6, somewhere here. No, no. Okay. Ah. Okay, it starts somewhere here, and then from there, it goes to 1.3, say somewhere here at pi over 2. At pi over 2, as a matter of fact, let me see. At pi, that is going to become -1. So at pi gets its largest value. Because I plotted that one, okay? And then it goes down at 2 pi will go like that. And then it's gonna go like this, and it's gonna stop at the maximum value here. All right, it's smooth function, does not have a peak, it's smooth, all right? So I have to show it. It's only, so it's gonna go like this somehow. Huh? No? So maximum at pi here, minimum at 2 pi, and then maximum here. So it's gonna go like this. All right, something like that. I think it's good to find it. And so then, this, if the line is longer, this will repeat. Nothing is gonna change. If the line, say, was not 3/4 of the wavelength, but it was 5/4 of the wavelength, there was like something else, it would still start always at the load here. So for example, if my line was longer, then, and I had more wavelengths in the line, then it would always start at the same location where it starts for the load, but it would be extended to the left. as you go to the source, all right? So in any case, for that, that's how it looks. So I have a V max here, and it's normalized. Obviously, I have a V min here. Now, on the basis of that, what you see is the following. If you run a lot of experiments like this and you change the value of the load, you will see that the peaks go higher and the dips go lower. So the distance between the minima and the maxima becomes bigger when the load becomes bigger compared to Z naught, and become the distance between the peaks and the valleys goes smaller if your load goes closer to Z naught. So practically, what I'm saying is that if my load here in all of this, if my load ZL were 1, okay, that implies that my gamma L would be 0, and that implies that my V minus of Z would be 0, which then it implies that V of Z would only be my V plus of Z, all right? Which then tells me that my V of Z would be equal to a constant, which is that, just that. So if I were to plot this V of Z, I would find a constant line, a straight line, and in that case, it would look like this. So, and that would be when ZL here normalized is 1. While this one here, this one is when my ZL normalized is 2. Okay. So now that tells me that how do I understand, how do I get, because obviously here I'm not getting a unique number to show me how much the reflection is compared, all right, to the optimal case where I would have no reflections. Because ideally, you remember what I said? Ideally, if I have a source, I would like all of my source to go to my load. I don't want to reflect anything back from the load because power is expensive, especially power at high frequencies. So that means that I have spent a lot of money to generate power at 5 gigahertz. So for a 5G, you spend a lot of money to generate that power. So the worst you can do is to reflect it away from the load. Your load is your antenna, for example. Usually antennas, when they operate at the center frequency, are resistive. They have a resistive value. All right, so the input impedance to an antenna is a real number, real in ohms. Okay, so I'm gonna send all of my power to my load. Let's assume that this ZL was the input impedance to an antenna. Now it tells me that if this ZL normalized, my antenna has 100 ohm impedance, my transmission line has 50, that it tells me that one third of my voltage is going to be reflected, and in terms of my power is going to be 1/3 to the second power. So what I would like to do is to have a unique number to tell me how far away I am from my optimal situation, which is a complete match. And this number is called the voltage standing wave ratio. So people have identified this. So the voltage standing wave ratio. It's a very important number, and we show it by VSWR. So if I go, for example, to purchase a component from a vendor, And that, let's assume it's a low noise amplifier or a filter. I'm gonna put it in my circuit. They will tell you how much the VSWR is gonna be at the input port. They will tell you that when the output port in that is matched, the input port is going to give you something. And this VSWR is going to give you a good idea of how far off your design is from the optimal. So, so just a second. Let me see something. Okay. And the optimal VSWR, the optimal value of, you will see what it is from the definition. So VSWR is nothing else from Vmax, sorry. Ah, So people were smart to find one unique number, Vmax over Vmin. What is Vmax? Vmax is this one up here. So this is the line that shows me the Vmax, and that Vmax repeats. I only have one Vmax, all right? And Vmin is this one. So the Vmax over Vmin shows me this VSWR. How much in this case is the Vmax over Vmin? I can find it. Vmax 1.33, Vmin is 0.67. So if I do this one, Vmax 1.33, oops, sorry, there, 1.33 divided by 0.67 divided by 0.67, 1.98. Yeah. So VSWR here is 1.98. How much is the VSWR at here in this case? How much is the VSWR when I have a perfect match? One. Because it's a line. Vmax and Vmin, if you straight line, are the same. So I have, for a matching case, so for perfect match, I have VSWR to be 1, all right? When is the worst matching condition? Would you be able to say? You know when is the best thing to find it? On the Smith chart. So now if we have a few minutes, I would like to go with Don. We are gonna see on the Smith chart, now you have to think about what is the worst, all right? But on the Smith chart, it's gonna come immediately. What is the worst? The worst case for matching is if your load is only reactive or open or short. Why? Because your reflection coefficient gets its maximum value. How much is the maximum magnitude of the reflection coefficient? 1. Wherever it goes, comes back. Okay? So if it is 1, then the value you will also find out, what I'm not going to do, but you can prove as a matter of fact that this is 1 plus gamma L, 1 minus gamma L. All right, so if gamma L is 0, which is in the case of a perfect match, then your VSWR becomes 1. If your gamma L, and as a matter of fact here, if your gamma L becomes 1, like it is in the case of open, short, or a complex or a reactive load, so no real load, not real part in the load, open, short, or purely reactive, they give you a reflection coefficient that has a magnitude of 1. In that case, what happens to VSWR? Infinite, theoretically. That means VSWR. And in reality, the best VSWR that you're going to see out there is going to be 1.1 for a frequency range. They will tell you that my filter works between 8 to 10 gigahertz. And for this case, my VSWR, if it's a good filter, it's going to be less or equal to 1.1. So there is no place in that frequency range where your reflection coefficient is higher than whatever this is going to be. So you can find out what will be the value, the magnitude of gamma L for a VSWR to be less than 1.1. All right? So, but they don't give you reflection coefficient, they give you VSWR. And you know you have to be very, very close to 1. 2 is hugely bad, as you can see. 1.1, 1.05. If I start going to 1.3, then I'm getting a little concerned. These are the values you're going to have in mind. But this is how now you're going to solve this problem. The other thing that I would like you to do also, which I'm not going to have ready until tomorrow morning, but the other thing is to plot also the current that you can find. All right, now that you have your V, you can do the same and find your current directly from here. But well, maybe I will ask you only for V. So I don't put that much time, effort on this since you have the homework. But you can plot it to see how it looks. All right, so you get a feel. Any questions about this? So what we are going to show next time is all of this, it took us an hour to do. On the Smith chart, it's going to take us 5 minutes. So that's what you get. But this is good to know how it comes out, all right, obviously, mathematically speaking. Any questions?
Basically, what we were computing here was the magnitude of the voltage over the
Yes.
value of V naught plus.
Yes. And if you assume that V naught plus is 1, that's what you get. Yeah. But for VSWR, V naught plus does not matter because you divide two numbers who have V naught plus there, so it gets out of the picture, right? VSWR only depends, as you can see from here, on the load from this one. Any questions? Any other questions, rather? Yes.
So in this example, we used a voltage source that was ideal and didn't have
Is internal impedance.
internal impedance. How would that affect the V over V?
It will not reflect at all. It will not change at all this pattern. All right, it will change only V naught plus. It changes, it affects only how much of the total power that the source can generate eventually goes into the input port. All right, so ZS, if your input, if you manage to, let's assume that my source could generate 1 volt, ideally. And then, however, has an internal impedance of 30 ohms or something, all right? And then I manage to match my line. So in the input of my line, I manage somehow to do a perfect match here at the input port. If my V naught has an internal impedance, it's going to limit how much power is going to go, because part of it is what it says is that part of it is expended internally in the source. So the source has an internal impedance because the source is not just a transistor. I mean, a transistor cannot produce anything without all of the circuitry around it. And if you start placing circuitry around the transistor, then that circuitry takes up some of the power. That's why internal impedance is there. Usually it's real plus imaginary. And then that tells you it limits really. So instead of being an ideal source where, you know, anything that can, the transistor, the maximum transistor could produce, it comes into it, is not. A real source implies the internal impedance only part. So like maybe 10% of the power is gonna go internally. If it's not a very good source, 20% of the power is gonna spend internally, and only 80% of the total would show up at the input port. That's what the internal impedance does. But it does not affect anything inside the transmission line. Any other questions? Okay, so as I said, I will try to place this on up today, this information, but it will be until tomorrow morning that I will do the small problem that you can just play it. You can do it by hand. You can do it with a calculator. You can do it in MATLAB. Where I just want you to just play with this expression a little bit. Okay? All right. Thank you. We'll see you on Sunday for office hours. Thank you.